don't remember when we took a break, so let me start anyway. So I skipped few slides. If you want, you can look at them later. Essentially was discussion of droplet formation due to instability of the liquid jet. And I came to this picture just to indicate that the interest in droplet combustion or droplet burning is that because when you have a spray, you have a variety of things that could happen. You have, atomization of the liquid jet into drops, and you can have these drops evaporate, and you have a diffusion flame outside that burn with the oxidizer. Or sometimes you have a cluster of droplets burning together, or you can have a singular droplet burning individually. And so whatever you're doing, understanding what's going on with a single droplet is valuable to put a bigger picture together. So the droplet problem is treated by assuming that the drop is a sphere. We are going to assume it burns in a quiescent oxidizer. So you have the drop that vaporizes, fuel vapor emanate from the surface. Of course, the drop shrinks as it evaporates, and the fuel vapor meet oxidizer outside, and it burns in a diffusion flame around it. And I mean, of course, we are assuming a spherical symmetry, neglecting gravity, which will tend to change the nature of the flame or the shape of the flame. And we are assuming that the droplet is formed of a single component fuel. If not, then there's interesting question that can happen because different component can diffuse towards the surface at a different way. And so it's not what vaporizes at the surface depend on what's happening inside the droplet. So of course, it's quite a complicated problem. So that simplifies that discussion. And then the first thing that I want to start is that one can write an overall mass conservation balance of or mass conservation of the droplet. So this is the volume times the density, the raw liquid, the density of the liquid. The time rate of change of this mass is equal to the mass flow rate outside that leaves the droplet, the gas that leaves the droplet, denoted by m dot. And note that this mass flow rate is relative, of course, to the moving droplet, which exceeds as you as time proceeds. So if you so I'm talking about just the droplet, no flame for now. So just pure vaporization. So when you differentiate this, you get, of course, only the radius change. The liquid density is nearly constant, so treated as constant. So you get Rs squared dRs dt, and the mass flow rate is the area multiplied by the gas density multiplied by the relative velocity. And so if you rewrite this as an equation for the radius, you get the ratio of the density of the gas to the density of the liquid, multiplied by V minus dRs dt. dRs dt is the rate that the surface recedes or changes. Now, in general, the gas density is much smaller than the liquid density. So that ratio is very small, smaller than 1. So among those two terms, which are explicitly written here, this one is relatively much smaller than the first one. And so the rate of change dRs dt is, can be approximately equal to the density ratio minus V, okay? So if I know the velocity of the gas leaving the droplet, which have to be analyzed from the gas phase solution, then I plug it here and I get a history of the droplet radius. In other words, it shrinks until it goes to zero and everything is vaporized or everything is consumed. So this is one important relation. An important assumption here, as I said, was that the density ratio is quite small. And that leads to what is known as a quasi-steady approximation, which I can follow systematically by writing all the equation as necessary, and this parameter appears all the time in front, this ratio appear in front of the time derivatives. And so the time derivatives are essentially small compared to convection and diffusion. Basically what it says is that the droplet recede very slowly, and whatever happened in the gas is, can be computed from a droplet of a given size, and then for a different size, then from a different size, okay? So the size is become like a parameter. And that's the essence of this quasi-steady approximation. So typically the ratio is of that order. The droplet recedes slowly, and m dot or rho gas V can be determined from the steady equation of in the gas phase. And then once we evaluate this, we come back to this relation to determine the history of the droplet. The same relation, by the way, can be obtained from the interfacial condition that I show you in the first day, that you obtain by evaluating a small control volume that surround or that enclose the interface, writing the equation, conservation equation on one side and another, taking the limit that the control volume goes to zero. And when you do this, you get, again, of course, you have to assume rho gas over rho liquid is small, like I did before. You obtain the same equation. But you also obtain conditions for the species equation. What are the proper boundary conditions on the interface on the surface of the droplet? So for example, this is one of the relations that we derived at the time. Omega I hat was the surface reaction if such chemical reaction occurred. So if it doesn't, as we assume for this vaporizing droplet, then that's zero. We are assuming, of course, that inside the droplet, the velocity of the liquid is zero. It's not moving. In reality, there would be some motion imposed by various things. Various reasons could lead to some motion, but it's a first approximation. It's a reasonable assumption to do. Inside the liquid, diffusion is negligible. Really, diffusion is more important in gas than in liquid. So both those V, that's the diffusion velocity, the velocity in the liquid is zero. And so nothing is, so that's in the liquid. In the gas, what you get is from Fick's law, you use that rho yi Vi is proportional as we did to the concentration, to the gradient of the mass fraction. And so here is the equation now in the liquid and the gas. So in the liquid, you get rho liquid, Y liquid or Yi, which is, let's say, going to be 1 by assumption, multiplied by Vi, which is Rs dot. Vi is the velocity of the interface, which is here is Rs dot. So it's the only thing left in the liquid. And in the gas, you have the relative velocity, and you have the diffusion term In other words, what you have is the velocity v, this is the rs dot, and this is come from the diffusion. Anyway, even though I'm showing the details, the idea is that you can derive from those interfacial condition or from those jump relation across the interface the proper boundary condition that you want to use for the droplet. If we assume again that the droplet recedes slowly, then this term is negligible, and you end up with this relation, which tells you that if you want the convection and diffusive fluxes of fuel outside of the droplet is equal to rho gas times the velocity. It's the velocity that leaves the surface, okay? For the oxidizer, the same thing, but it's equal to 0 because no oxidizer really penetrate the surface. Nothing come out, no oxide come out of the surface, so to speak, okay? So those are the two boundary conditions. And the third one is going to come from the energy equation. And the important thing in the energy equation turned out to be, well, you can, again, check term by term, but what you get here is the enthalpy in the gas, H gas, rho gas, multiplied by the relative velocity. And this is the enthalpy in the liquid, H liquid, rho liquid times Rs dot. There is no velocity here. And then the conduction, well, you have lambda, the conductivity of the gas dt dr, but this is on the plus side, on the outside the droplet, whereas here it's inside the droplet, okay? And if you assume that it recedes slowly as we did before, then it simplified to this. In other words, the Rs dot get killed. And the difference here, so that's what you end up with. So you have here a difference between the enthalpy of the gas minus the enthalpy of the liquid, which is essentially the amount of the latent heat of vaporization, okay? So this is a quantity that you know, or you can find tabulated. And the equation then is the difference in the gradient of temperature towards and inside the droplet is balanced by this, by the latent heat of vaporization. Inside the droplet, well, in principle, you have to solve the heat conduction equation inside the droplet. If you want to avoid doing this, then you have to estimate it somehow. So what you can estimate that all the heat conducted inside the droplet go to heat up the droplet. So it changes the temperature of the droplet. It's one of the approximations that has been used. And so this is this term here. And often this is by itself neglected where the latent heat of vaporization is adjusted to account for the heating of the droplet. To make the story short, the simple boundary condition, that we want to use in the discussion that will follow is simply this. Lambda dt dr is equal to rho v times the latent heat of vaporization, and it's not written here yet. It will be in the next slide. So we want to solve now the gas phase equation. Remember that because of the quasi-steady approximation, we're solving steady equation. So for the time being, I'm going to call the radius A and the density rho. And when later, when we want to go back to discuss the receding of the droplet, I will rename it as RS and so on, just a matter of notation. So in spherical symmetry, this is conservation of mass, balance equation of the fuel of the oxidizer, energy equation, Actually, everything is written here in dimensional form. Again, the reaction rate. Far away, you know that the temperature is T infinity, density rho infinity, you know those value. There is no fuel, and there is some amount of oxidizer. And there is one more condition that is needed apart from the boundary condition that I have mentioned, and this is usually one has to assume that the phase change is very fast, and so then the relation between the partial pressure and the temperature is given by a relation known as the Clausius-Clapeyron relation. But even that, we want to simplify and assume that the temperature of the droplet is known, and therefore the droplet, the surface is known, and I will call it T sub B. Okay, so in more general circumstances, the problem is yet more complicated even due to that. Okay, so here are the boundary conditions. We derived those two relations a few minutes ago, the energy equation as well, and T equal to TB. Those are sufficient conditions to determine the problem, okay? You can count equation and boundary condition, and that works. We want to put it in dimensionless form, and so the mass conservation, the derivative of R square OV 0, meaning that that quantity is M, a constant that I want to evaluate, and need to be determined, in other words. And then you have equation for YF temperature, YO temperature, and so on, and those are the conditions, okay? And because it's put in dimensionless form, capital M is essentially M dot divided by 4 pi and scale with A lambda over Cp. And the Damn-Color number here, which appear in the reaction term, again, when you use the non-dimensionalization, it takes this form. What's interesting to note about it is two things. It depends on the radius, A squared. It's proportional to the radius. And in fact, is also proportional to rho infinity, well, square, which means it's also it depends on the pressure. So that's two things that should be noted for later. Another thing is that the heat of combustion is little q, as notation that we have used before. The latent heat of vaporization is, I called it LV, okay? And they are both scaled with CPT infinity. So, actually, that's what I wanted to say. Damn-Color number is proportional to A squared and to the pressure, right? Pressure through density from the equation of. You know outside the pressure, it determines the Damn-Color number. You change the pressure, different Damn-Color number, or the radius. Okay. So, and in this presentation, we will assume that the Lewis numbers are 1 for simplicity, but we know how to deal with non-unity Lewis number because, after all, it's a diffusion flame. So we have seen earlier today how to deal with this. Okay, so the first thing to do is to solve this equation for omega equal to 0. Note that the operator here, when Lewis number is 1, it's something like m over r squared d by dr minus, well, 1 over r, the Laplacian in spherical coordinate. And it has an exact solution of the form e to the minus m over r. So in the case that the Damn-Color number is 0, namely pure vaporization, you get YF, you get YO, you get the temperature satisfying the two conditions. And when you also use the temperature at the surface and all the boundary condition, you get an expression for M. M being the burning rate or the mass flow rate. This are the sketch of those graphs, the fuel go down to 0. The oxidizer from a constant value diffuse toward the droplet, and this is the temperature. And in dimensional form, if I rewrite this capital M, it gives you the vaporization rate, which is given by this constant, come from dimensionalization, the log of 1 plus, and this becomes CTT infinity minus TB over QV. Remember, QV is the latent heat of vaporization. And so there is a coefficient here, which is known as the transfer number, which is this ratio, the ratio on top to here, CPT infinity. The numerator is the impetus for transfer. If you have a higher temperature far away, it will conduct more heat, it will vaporize, it will improve or increase the vaporization or the transfer. The numerator is the resistance to transfer. It's the heat of latent heat of vaporization, latent heat taken to vaporize the system. Clearly, a solution will exist only when this constant is positive, otherwise the log is negative, and that means that you have to have heat conducted towards the droplet for it to vaporize, which of course makes sense. The next thing is to do the same problem, but with d goes to infinity. Since the Lewis number were assumed equal to 1, then we can use the coupling functions, and we have seen already a couple of examples how to do that, and so immediately you get the fuel consumed past the reaction sheet, the oxidizer, and the temperature. And that's really the picture that you've seen here. They are all consumed at the location RF. It remains to determine the burning rate and the flame location, and we have enough boundary condition to do that. When you apply, for example, those jump relation across the reaction sheet, you will get those two relations. Here is M, which is related to the burning rate, and here is the flame position. And once you know that, you evaluate the temperature at RF, and you get the flame temperature, of course. Okay, so we have all those relations. Putting the burning rate in dimensional form, now you get this form here, similar to before. Again, we have a transfer number, but this transfer number, I put it with a subscript C for combustion as opposed to V for vaporization. And the difference is, of course, the heat release. So the impetus for transfer is not only the heat conducted to the droplet, but also the amount of heat released, which give more heat towards the droplet to vaporize it. And the denominator is the resistance to transfer. It's again the latent heat of vaporization. And the flame standoff distance is given by this relation, and it can be verified that, well, RF, the position must be bigger than A, which is the size of the droplet, which implies that this condition here, which is not too restrictive because Q is always, not too, but it's not restrictive because Q is typically bigger than the latent heat of vaporization. Anyway, the relation, so we have relation for the burning rate with for the vaporization rate, we have for the burning rate, we have a flame position, and we have the flame temperature. And now, again, we go back to this picture because it's quite relevant for typical diffusion flame, including this droplet problem. And what we see is that we have here the Berg-Schumann limit, which we discussed today and now. we have here the limit d goes to 0, which is the vaporization limit. We have seen that we can compute part of that curve earlier today by using the asymptotic theory. In fact, we can also compute part of this curve. I mentioned it, I think, earlier also, although I did not discuss it. The difference is that here you have to start increasing or having a weak burning until suddenly it shifts to a fast burning. So again, we have turning point that describe ignition and extinction. And in terms of the Diamond-Coulomb number, they can be interpreted as such. Remember, D is proportional to the droplet size. So a smaller droplet, and smaller droplet will burn slower up to a certain point where maybe it's too small, it just, the flame around it is extinguished, okay? It can extinguish before the droplet totally vaporizes, or you can also have an ignition, which is often referred to an auto-ignition. In other words, the radius is such, or the pressure, in fact, is such that it's sufficiently high that the droplet will ignite by itself, okay? So you may have this auto-ignition, auto-extinction situation. Of course, it depends on the condition, but this is the general picture is here. What about the droplet history? So now we go back to the relation that we derived earlier, and remember that we have to replace A by Rs and rho by rho gas. So m dot is now given by this expression, but since we know that it's equal to the log of 1 plus b and so on, so we can put it in the expression, and we get that the Rs dt, which is equal to the density ratio times V, is going to be inversely proportional to Rs. And the constant of proportionality here is this constant K. And so the differential equation is 2Rs dRs dt. This is the same thing as the derivative of Rs squared. So if you integrate it, you get Rs squared equal the initial radius minus Kt. So the radius squared decreases linearly in time. Usually it's written in the literature in terms of the diameter rather than the radius, and it's referred to as a d square law, where the d indicate diameter. In other words, the droplet diameter square decrease linearly in time, and so it's completely evaporated, or when at time t equal 1 over this capital K, where this capital K related to the little k before is given by this relation. So it gives you an indication of the lifetime of the droplet. And it turned out that these are quite correctly, they capture experimental observation, except, of course, for the short initial period that follow ignition in an experiment. These experiments are mostly done under microgravity condition, which can be done either at low pressure, where the Grashof number is small, which is practically saying that the gravity effects are small, or you can do it in a drop tower experiment. They have been in a variety of ways. Otherwise, the flame near the droplet have a more teardrop shape because of natural convection. It's no longer spherical symmetric, and it's more complicated. Now, you can similarly also describe the combustion of a solid particle. So suppose that this is the solid with some distance Rs, and you assume there is a diffusion flame standing off the particle or of the solid, and let's say the solid gasify, similar to the vaporization process, and the vapor interact with the oxidizer, and the flame, there is a diffusion flame, it burns at a flame. Then the result will be similar to the previous analysis. If one assumes that the flame stand of this is sufficiently close to the surface of the particle, which is what I have assumed here, then log of 1 plus b is approximately this. In other words, it's dictated by the amount of oxidizer that you have in the ambience. And so you can write an expression for the burning rate, and it's often referred to as the diffusion control limit because it's controlled by diffusion, essentially. The other, in writing here, it's often, you will see that often the literature they use in the burning rate, the diffusivity of the oxidizer, because everything really is dictated by the oxidizer, the amount of oxidizer and the diffusivity of the oxidizer to work. Of course, this to obtain this systematically from the previous analysis, it requires assuming the Lewis number is 1, because previous analysis we have a lambda over Cp, and so to replace it by rho d of the oxidizer, it's a unity Lewis number. Otherwise, there might be some small effects that may influence that. And one can similarly derive a d-square law, which is given here. So, and evaluate the lifetime of the droplet or the particle, okay? So it's a very similar to the condition or to the example we did before. However, there may be a situation where the burning occurs on the surface of the particle. In fact, sometimes it may occur, if the particle is not a solid with pores, it may even occur in the pores. So you can approximate this by saying that the reaction occurs on the surface. And if that's the case, then m dot is not determined by the gas phase, but it's determined by the kinetic on the surface of the particle. So m dot is going to be some proportional to amount of oxidizer, right? Like in any other reaction, and that's the surface area. And Ks is the kinetic or the dependence on the temperature of the surface, which is an Arrhenius function, okay? And so this is a different limit. It's the kinetically controlled limit. If we now use m dot and evaluate the lifetime or the history of the droplet size, you don't get a d-square law, you get a d to the 1 law, okay? In other words, d decreases linearly, not d squared decrease linearly. So and the lifetime depend now on the kinetics as opposed to before, primarily on the oxidizer. So you have like 2 different behaviors, and it depends, therefore the lifetime depends if it's diffusion control or kinetic control. So you can determine a coefficient or a sort of a Dam-Colon number, which is the ratio. I say sort of because it's not a flow time divided by reaction time, but it's the diffusion time divided by kinetic time. And it tells you, it's given by this expression. So we see large particle or higher ambient temperature, okay? Large D naught and larger TS gives you a larger value here, is associated with a larger Dam-Colon number DS, which means it's diffusion control, because kinetic diffusion control is more important than the kinetic time. Small particles and low ambient value, it's more kinetic control. So you see in a furnace that have many particles, you can have some particles that are large, they burn in a diffusion control, but when they become small enough, they become kinetically controlled. So it's a complicated system in general to accommodate for all those, but anyway, it's interesting to note that. An analysis that showed the behavior around a carbon particle, where in a carbon particle, the chemistry goes that you have carbon can burn with oxidizer to give CO, or it can burn with CO2, produce at the diffusion flame to give CO, and then you may have a diffusion flame, or you may have a kinetically controlled situation. So you have here the two damp color number that arises, one due to the gas phase and one due to the surface reaction. And the only thing I want to show here is that you can have a transition from one behavior to another. In other words, it may, when the gas phase damp color number increases, you may be burning on the surface, and then when it increases sufficiently, then a diffusion flame is created, or vice versa, depending if you reduce the damp color number. But the situation can also go the other way around. And so all I wanted to show here is that you have a variety of possibility that would occur given the multi-type of phenomena that would occur. I think it's the end of this discussion. I know I was trying to be brief. I wanted to close it on time this day. Not tomorrow I have a longer discussion to make. So particularly on flame instabilities, but also on turbulent flame. So I hope I will be able to cover it all. If not, I may stretch or I may contract the break time. So yeah, thank you, and I'll see you tomorrow.